give a brief introduction to us. After that, we get started.
Sure. Do you want this?
Good morning, everyone. Welcome to Day 5 of the ACM Inter School 2025. Today we have with us another respected resource person, Dr. Manas Thakur from IIT Bombay. Dr. Manas Thakur is a faculty member in the Department of Computer Science and Engineering at IIT Bombay. His primary research interests lie in compilers, programming analysis, formal methods, and software systems with a focus on improving software correctness, performance, and reliability. He has published extensively in leading international conferences and journals and actively collaborates with academic industry partners. Dr. Thakur is also passionate about teaching and mentoring, contributing to advanced courses in programming languages and systems. He earned his PhD from IIT Kanpur and contributes to guide research scholars. IIT Madras, and continues to guide research scholars and lead projects that advance foundational and applied aspects of computer science. On to you, sir.
All right, thanks Ishan for the introduction. Good morning, and I need to know all of you as well. This is an interesting school, right? You have a different face standing in front of you every 2 days. But I am here for the longest time. I am here for 2.5 days, so I should know you more. We'll follow one algorithm. Are you also attending the winter school? No. Okay. So if you, okay, sure. So if you are not a volunteer or a TA or an organizer, your algorithm is to stay as close as possible to the front. Okay. So if you see a row in front of you and all of your friends can accommodate in that row, please shift. It's okay. First 2 rows I can give an exception, your wish. All right. We have several sessions here. We have enough time. So I would prefer to know you a bit. We can spend 2 minutes, 2-3 quick minutes in the beginning to just have a brief introduction. Okay. Just say your name at least. Where are you from? And if at all you have a solid reason, please tell why are you interested in learning compilers. Okay, so please add one line on that after your name and maybe the institute or the place where you are from. Okay, you can start from here. Kshitij, you are from IIT Dharwad. Okay. Okay, so you are interested in systems in general. Yes, good. You can keep sitting. Okay.
And I have interest to learn everything of basics of software, so I'm good.
Okay, good. You have to be loud enough. Yeah, please use the mic. Thank you.
I am Nikhil from ISR Bhopal, 3rd year BS. So I am interested in operating systems and want to know how codes are compiled. So I am learning compilers.
Okay, good.
Hello sir, I am Shreyas Hegde from Dayanand Sagar College of Engineering, Bangalore. I am interested in compilers because I love to know what is the nitty-gritties of the programming language and all. And along with it, I was inspired by Ashutosh Pandey. So yeah.
Good. Ashutosh is doing good work.
Hi sir, I am Aditya Medne from IIIT Gwalior, and I am originally from Nashik, Maharashtra, and I am interested in compilers because I think it's fun.
Because?
It's fun.
It's fun. Yeah, I agree. Go ahead.
Hello sir, I am Krishnakant Patil from PCCOE Pune, and I think I love compiler because it shows how the things work behind the scenes.
Good.
Hello sir, my name is Rushikesh and I am from Pimpri College of Engineering. I joined this school because I wanted to learn something different and know how the things works before coding, like after coding, what the actual thing happens in the behind the scenes. So that's why I joined this here.
Sure. I hope you are learning that from last 4 days too.
So my name is Srinivas. I am from Dayanand Sagar College of Engineering, Bangalore. I chose this compiler because it was interesting.
Hello, sir. I'm third year student from Triple IT Nagpur, and I love low-level programming. That's why I like to learn about compilers.
Oh, one of your instructors was at IIT Bombay two days ago. I met somebody from Triple IT Nagpur 2 days ago. Anyway, go ahead.
Hello everyone, my name is Dhruva Narayan. I am from Triple IT Nagpur, third year. I am interested in compilers because it shows like how the codes are optimized behind the scenes and all. I like optimizations.
Okay, low-level optimizations. Pass it on.
Hello sir, I'm Arnav from IIT BHU and I'm interested in compilers because I think they are smart systems.
Very good.
Hi sir, my name is Mohammad Nihal. I am from Adi Shankara Engineering College, third year, computer science students. I chose this school because I want to learn about compilers. Thank you.
Yeah, continue.
Hello sir, I am Sanjana Elizabeth. I am from Adi Shankara Institute of Engineering and Technology. I was just curious to learn more about compiler design.
Okay. So you all are computer science students, right? Okay. That's one thing I want to know.
Hello, my name is Fatma Rena and I'm from TKM College of Engineering, Kollam, Kerala. And I'm just curious and I want to explore this field and that's
Hello, my name is Krishna. I am from Adi Shankara, Kochi, Kerala. I joined this school because I found this topic interesting and wanted to explore more.
Hi, I'm Dhyanesh from SRM Institute. So I just wanted to learn about compilers because to learn the back end rather than the front, it's much better, easier to understand how the programming goes.
Sure. Today onwards, we are going even more back in the back end.
Hi sir, myself Jay, I am from Nellore. I am studying my BTech in Madurai currently, and I joined this course because I wanted to learn the difference between what I learned in my course and how it will be applied in the real world. So I joined.
Okay, we'll have enough examples.
Hello sir, my name is Jairus Joshua. I am from Andhra. I am studying in Madurai, Kalaslingam Institute. I joined this course because I want to know how the high level language is converted to the low level language into the CPU architecture.
Hi sir, I'm Kshitij from SRMIST. Yeah, initially I thought I knew compilers in an abstract way, and when I saw this course, I thought how vast of a sector it could be. And since I joined, I've been like noticing that it's a very huge sector, and there's a lot of work to do in this sector.
I agree. Okay, you have a mic.
Hi sir, I'm Merlin from Tyagaraja College of Engineering. I'm a data science student and we don't have compiler design in our curriculum, so I just wanted to explore a new topic.
Sure. System stack is not done until you learn compilers.
Hi sir, I'm Kavya Sri. I'm doing integrated MSc data science at TCE Madurai. The same, this was not a part of a curriculum and I just want to explore how the compiler works.
What if I tell you now there will be a test which will check how many names you know? Anyway, go ahead.
Hi sir, I'm Sri Darshini from Tyagaraja College of Engineering. So I'm an MNC data science student. So I want to learn new things about the compilers after this school.
Hi sir, I'm Sri Vashini from Tyagaraja College of Engineering. This was different from whatever we usually study, so I was interested in exploring how it works.
Hello, I'm Lukman and I'm from PSG College of Technology, Coimbatore. I am pursuing MSc in data science and I got interested in compilers after realizing the impact that they have, the scale at which they operate.
Okay.
Yeah.
Hello sir, I'm Aishwarya from PSG College of Technology. I'm doing my second year in MSc Theoretical Computer Science. I just wanted to know a lot more about what happens behind the scenes with the code that we wrote.
Hello sir, I'm Yalini. I'm from PSG College of Technology, Coimbatore. I'm doing MSc Theoretical Computer Science, second year. I just want to know more about the compilers and I'm curious about it.
Sure.
Hello sir, my name is Keith Pereira. I'm from SRMIST. I'm in my third year of CSE right now, and I have worked with the Shakti processor. So I want to know more about how code is going from our high level languages like C and down all the way to the assembly that I see when I do OBJ dump.
So you have written a lot of C code.
Yes.
Hi sir, I'm Jake. I study here at SRM only. I'm doing my third year. I took this course because I wanted to see what happens beyond programming code.
Hello sir, I am Sanchita Sakre from PCCOE Pune and currently pursuing second year in CS. So I like to explore things and just wanted to know what is going on behind that commands.
Hello, sir. I'm Mohana Priya from SRM. I'm a third year CSE student. I want to know how compilers help in programming.
I'm Rayana. I'm in third year CSE at NSUT Delhi, and I basically had some coursework at my college on compilers, so I wanted to know more.
Good morning, sir. I'm Kalaivani from SRM University CSE Core, and I want to know the fundamentals of compilers and how it works in the backend. And I'm here to learn with hands-on practice.
Good.
Hello, sir. I'm Ruchi, first year PhD student from IIT Roorkee. I have just started my research in compiler testing.
With Avnish?
Yes, sir.
Avinash.
Avinish Pandey.
Avnish Pandey. Yes.
Hello sir, I'm Jayashree, first year PhD student, IIT Bombay. Like Ashutosh for him, it's Pradeep Kumar for me, via LLVM Social Bangalore. So hopefully I reach one day to do good work just like them. So ACM compilers for that.
Sounds good. So see, many of you are here for, many of you had some exposure with compilers is how I understand it. And those of you who did not have as well, last 4 days you have learned several things about at least machine independent optimizations, analysis and so on, right? Can you name a few optimizations that you have learnt about in the last few days? Well, that's an analysis. What optimization will get enabled by live variable analysis? Dead code elimination, common sub-expression elimination you have learnt about. So I hope you have a general idea about how fixed point analysis work, right? You must have seen either Professor Khedkar or Professor Karkare would have shown you some examples of data flow equations and so on, right? Today onwards we would see several more optimizations and many, well, there will be a good mix. There will be some optimizations that we would study in this session that don't require much of data flow analysis that you have learned. Okay, they are peephole optimizations, very simple to perform pattern matching based optimizations. We will learn about them. That's the simplest topic of your school. So Monday morning, don't worry, it's easy. Okay, and then we tomorrow would learn about several more optimizations at the memory level that require integrate data flow analysis that you have learnt about. Okay, so we would talk about optimizations that are simple first, but they are effective as well. And then we will also talk about optimizations that are a bit complex, but then they are very impactful in tomorrow's session. Other than that, we would talk about other things that a compiler has to finally do to generate assembly code. Why do we generate assembly code? Why not binary directly? We say, right, low level code. Low level code is assembly. We stop there. Why do we stop at assembly? Kuch to rehem karo janab. Okay, so there is, if you had to learn binary while writing a compiler, you will struggle even more. That's the simple reason. There is an assembler, let it do its job. We will generate English like assembly and be done with it. Okay, so our goal is to generate assembly, and as one of you said somewhere there, one of you said that you want to see how is it different for different CPUs and so on. In this course, the ACM Winter School, as we discussed, is quite vast and it expands across different instructors, which means you would also see things for different CPUs, but you will also see things for different hardware. I'm sure one day somebody will come from Qualcomm and tell you about how do they generate code for GPUs, for example, and so on, right? So you would learn several interesting features of machine dependent code generation. And when you generate code for a machine, you also need to know about that machine's instruction set architecture. Somebody told about operating systems and computer architecture. So you should know about your machine, its architecture, its instructions in order to generate code for it, and then you have to encode your low level program in some form that the machine can understand, or at least the assembler can understand for that machine, right? So that's where we would end. We would generate code also as part of these sessions today and tomorrow, okay? Or at least we'll learn about nuances of generating code. We'll do some hands-on. We'll have more hands-on than the last few days, just because now you're reaching at a level where you have understood various prerequisites for the hands-on sessions, okay? Did you get, just to ask few more questions, did you get instructions on setting up Docker and Java, and how many of you were able to do them? I mean, how many of you have successfully set up Docker on your machines? Okay. Those of you who haven't, we will spend some time, but I would like if you would have done it already or try it in the lunch session, ask your friends. You saw that most people in that column raised their hand, so if you haven't been able to do, you can freely ask somebody in that column and say, oh, help me out, okay? Ask them during the lunch session or something. Otherwise, we'll continue. Of course, we have teaching assistants here who would help and so on, okay? So, let's now begin. So, some of you specifically said you are interested in learning about the back end more. You have had some exposure with the front end already. So if you come through this standard figure that describes various typical stages of a compiler, this is where we are right now, okay? You have had some exposure to this block already. We will have some interaction with it in the days to come, but we are on this side now, not in that side, okay? Which one is more interesting? What do you think? Why is one of these sides more interesting? You have to keep talking, right? So I didn't ask you to tell your names just to remember your names. You also have to keep talking throughout the sessions. Then only it would be fun. Yeah. So why do you think the right side is more interesting than the left side? If that's the claim, or you can argue the other way as well. Yeah, go ahead.
Because the left side is basically we are only translating our code from what we wrote to a particular level that machine can start to analyze it.
Right.
On the right side, we are like analyzing it and optimizing it to a level that is correct.
Right. What's your name again? So as Aditya says, right, here it's primarily translation. Here it's translation as well as optimization, and probably Aditya likes optimization more. He likes to see, oh, I write a program that takes 5 seconds and the compiler does some magic here and makes it run in 2 seconds. So fun, 3 seconds accumulate for something else, right? So optimization is something interesting here, but then translation also from this side to this side doesn't map as it is. Okay, here you have the intermediate code, which is more or less, lots of semantics are still there in the intermediate code. So it's like in the same vocabulary as the source code most of the times. Whereas here you have to learn the vocabulary of the machine as well, right? So of course the process is similar, but there are some more challenges here on the right hand side. So the right hand side is more interesting, at least in my opinion and Aditya's opinion, and the right hand side is also more challenging to work with. Okay, so you have to make sure that you are asking enough questions so that you don't feel at the end of 2 days that, oh, we just learned about the challenges, we didn't learn about how to solve the challenges. You should learn both. Okay, that's your responsibility. All right, so for any given machine, let's say we have intermediate code in this form. It's some 3 address code. I hope all of you know about 3 address code by now, right? So we have, let's say, instructions in some 3 address code format, and then the code generator's output finally looks like this, which is in terms of the opcodes or the mnemonics of your hardware, right? So let us assume we have a hardware which has a load instruction, a multiply instruction, add and store instructions, and so on. How many of you know about addressing modes? Have you heard about addressing modes, right? So what addressing mode is required to write a number like this in a multiply instruction? Immediate addressing mode, right? So depending on the addressing modes of your hardware, depending on the instructions provided by your hardware and so on, you have to generate code over here, right? So immediate addressing mode, for example, allows you to supply some number over here in the instruction and so on, which means you have to basically know about the hardware before you could generate code, right? So that's one thing here. And now let's classify the roles of the code generator, or let's just list down the roles of the code generator over here. Well, first, as we saw just now, you want to convert an intermediate representation to a target program. You want to lower the level of abstraction, okay, using the primitives available on the target machine. That's what we saw just now. If I want to generate an LD instruction, the LD instruction should be available in the architecture, otherwise you won't be able to, in the ISA of my architecture, otherwise you won't be able to run it on the hardware, right? And then of course the biggest requirement is your program semantics should not change. So if the source program or the intermediate program adds 2 numbers without causing an overflow, even the resultant program in assembly should add those numbers without causing an overflow, or if it could, then you should have a way to know it and then take some action on it, okay. And well, so this is a requirement, and then the expectation is that the target code is of high quality, right? And by quality we mean, we land into optimization world here. We expect the execution time to be lesser than the original code, or / the space occupied by the program to be less. Well, when we talk about space, we may be talking about code size. On what kinds of machines do you think space is an important consideration? Embedded devices, right? So you don't have too much space here, neither to store code, and then you may have smaller chip itself, you may have less RAM, for example, and so on. So depending on the hardware, again, you have to decide what expectations do you want to target here. Well, yeah, energy may be important. I don't want my watch to heat up and cause me rashes on my skin, for example. These are valid requirements which the compiler has to take care of while deciding what factors to optimize for during code generation, okay. And then the code generator itself should be sufficient. This is not as important an expectation in all kinds of systems, but we don't want the code generator itself to take hours and hours. Usually it should scale as per the size of the program and so on, right? So these are some high level expectations that we have, right? So in reality, as we discussed just now, most problems in the front end on the left column that we saw are simpler, and most in the back end are a bit more complex, and many of them are NP complete or NP hard problems, which means you cannot come up with the best solution. You can never say that the code I have generated, or I have a compiler which will always generate the best possible code for this hardware. You can never claim it. You can prove it using halting problem. Search on Wikipedia, there is a theorem, a real theorem called as full employment theorem for compiler writers, right? So you can map down a simple program and basically map it to the halting problem and say, oh, if I could figure out that this is the best program for a particular architecture produced by a compiler, then I would be able to solve the halting problem, which cannot be done. And hence by contradiction you can say, oh, since I can never have the best compiler possible, I can always keep on improving the compiler, which means a compiler writer always will have a job, okay. That's the full employment theorem, which means, as we said just now, since we don't have the best solution, we may have to come up with approximate solutions, near best solutions, and we may have to use heuristics to come up with some solution that we are satisfied with. We will have to make conservative assumptions and so on, okay. All of you with me till now? Yeah, so just we should know what is the requirement of the block that we are looking into. That's what we are here for in the beginning. And then, as we said, well, if you want to translate from, let's say, Tamil to English, you have to know English first, right? So you have to know the ISA of your hardware. If I am translating for x86, I should know what instructions are available in x86, and then I should select instructions corresponding to my intermediate code or source code and so on, right? So instruction selection, which maps low level IR to actual machine or assembly instructions. It need not be a one-to-one mapping. It's not the case usually that if you have 10 instructions in the IR, then you will have 10 instructions in the assembly. Not necessarily the case, right? Similarly, for different architecture, you may have different generated code. I'll tell you, I used to use some code examples in my compilers courses, which were saved on in some directory on my machine, and suddenly one year I realized, oh, this doesn't look like what I am used to. the reason was I realized in the past year I had changed my system, and the architecture was ARM on newer MacBooks. The older MacBooks had Intel architecture, and I was surprised during my class when I saw, oh, this assembly I don't understand what happened. I realized, oh, it's a new purchase, right? So you can't execute code generated for one hardware on the other because the instructions that you selected are not available on that hardware. Okay. And then, well, you know that finally in the CPU, the basic unit of memory over which you operate, most of these instructions operate on registers, okay, which means you have to decide, oh, which variable to put in what register. That would be something which we would give a lot of attention to in today's sessions as well, particularly the post tea break session, where we will talk about interesting algorithms to perform register allocation. Interestingly, we will use liveness analysis again there, right? So that's why I asked in the beginning whether you have learnt liveness analysis. So, well, yeah, you remember when you generated 3 address code, you just keep adding temporary instructions, and the instructor on that day would tell you that, oh, don't worry about the number of temporaries that you create, just assume an infinite number of temporary variables available, right? So you can't really assume those many registers. Why can't I have a large number of registers on a CPU? Trade off with? That's one thing. And why that problem comes into picture? Yes. So you have a small sized CPU, right? It's very similar. If I have to walk from here to that side, whereas if I have to walk from here to your older tower, older tech park, then I'll take more time to go there. Right? It's as simple as that. We have a finite amount of space to fit close to the processor, right? And things that are closer to the processor would be accessible faster, as Jayashree was trying to say right now. So we do not have budget for an infinite or a very large number of registers, and hence we have to map these temporary variables to those registers, to the limited supply of registers. That's register allocation. Okay, so we want to make the best use of registers to some extent. What is best use here, we will again look into in the next few minutes, but I hope you see the problem. You have to select the instructions, and while selecting the instructions you have to decide what operands to keep in what register at what point of time, so that the hardware can work with them, right? Thirdly, you can also perform instruction scheduling, as we would see with an example very soon. You can also decide, most of the times your hardware are not just serial anymore. Even on a single core pipelined CPU, you have opportunity to run many parts of different instructions in parallel, and hence you can schedule and decide what to run before. If I have an instruction A equals B plus C over here, and if I have an instruction D equals E plus F somewhere down the line, it's not necessary to execute the later instruction after this former instruction. If you have resources available, you can decide to schedule them either in parallel or the later one before, and so on. We'll see lots of examples of why would you like to do that in today's and tomorrow's sessions. Okay, so a typical compiler also performs instruction scheduling. So see, instruction selection, register allocation, and scheduling, these are 3 typical things you can expect to learn from somebody who says, I will teach you low level optimization and code generation, but then you can also perform optimizations over here, right? So now we know that compiler understands the program, right? And when you lower from one abstraction to another, we said, oh, you should preserve the semantics of the program, right? So now when we are performing one transformation, I could perform more transformations. Why not build a backend which not only generates code, but also can generate optimal code in some sense, right? So that's why we talk about compiler optimizations. And as we saw just now, there may be various ways of optimizing code. It may be for space, it may be for time, it may be for energy, it may be for register usage. When we say space as well, it may be for the space occupied by the code versus the space occupied by the runtime process, and so on. So there are lots of considerations here. Let's understand them with an example that will also make you a bit more talkative and active. Okay. So the goal is to generate optimized code, and let's say we have multiple metrics here. Code size is one metric. Okay. So let us say that opcodes take 1 byte and each operand takes another byte for today's discussion. You have to solve something now. So just come into that mode. You have to assume that if I write an instruction add O comma B, A comma B, what's the size of that instruction as per this metric? 3 bytes, one for the opcode and one for each operand. We'll assume that whether the operand is memory, register, some immediate number and so on, everything is just 1 byte, just for simplicity. Right. And then we would also compute the number of registers. Okay. You know, various registers come with some constraints, like some register can be used only for floating point operations. So there are some such constraints as well, right? And then we would also talk about the speed of the code, and let's say our metric is again very simple just for this example, where we would say that instructions with a single operand take 1 cycle, instructions that have 2 operands take 2 cycles, and any instruction that accesses memory directly instead of accessing operands from registers, if it accesses memory directly, it takes 4 cycles. Why is it reasonable to have higher number of cycles for instructions that access memory? Sure, and memory is slower in general because of its physical properties, right? So memory is slower to access. Of course, you can have cache memory which is faster than the RAM, or which is faster than the disk and so on. But let us abstract all of them out and use a single word memory for today's session, where we would say, oh, if the instruction involves a memory cycle, it would take 4 cycles. All right. Remember these numbers, then only you will be able to compute what I ask you to do fast enough. Okay. How do you remember things? How does a CPU remember things? Puts into cache or registers. Put this information somewhere. Okay. If I ask you to remember something, you have to also keep it in your cache for some time. Take out your notebooks, take out your pencil, laptop, iPad, whatever. So let us assume that each opcode takes 1 byte, each operand another byte, and then let us assume that instructions with single operand take 1 cycle to execute. Some cycle could be millisecond, nanosecond, doesn't matter right now, some unit of time. 2 cycles is worse than 1 cycle and so on. Okay? Alright. So yeah, sometimes we may also optimize for power, energy, platform independence and so on. Let's not worry about it too much. So let's say the code generator is simple. You know, if you open, what's the famousest compiler's book? Holman. What's the other name for that book? Dragon book. So if you open Dragon book, you would see lots of algorithms for generating code. You would see tree tiling, you would see dynamic programming, lots of interesting things over there. If time permits, we'll learn about them, but if time doesn't permit, let's just learn about what actual compilers end up doing. Okay. Most compilers won't use complicated code generation algorithms as the first weapon. Okay. They would just perform a one-to-one mapping. They would take, oh, if it is an instruction A equals B plus C, I have to generate an add instruction for it. So let me choose the instruction add. A and B, if they are both variables, then let me just see which registers are they assigned to and then directly use those registers. Let me generate an instruction add R1 comma R2 if I know that A is in R1, B is in R2 before this, and that the result, let's say, is in R1 after adding both of them, right? So compilers would typically, most code generators would typically just perform a one-to-one mapping. They don't use many Dragon book algorithms in reality because they are complex, but we still have a way to optimize code after generating poor code. Okay, that's what we would see over here. So let's say we just use a one-to-one mapping, and if I have this set of instructions, this set of IR instructions to begin with, I generate this set of assembly instructions. Okay. Let's try to just understand them in the beginning. A equals 0 means, so you have to put 0 into some register first. Let's say my compiler allows me to only operate with registers, and then I have a store instruction, let's say, that stores R1 into the address A. A is some address, whether it's in my stack, whether it's in the memory, let's say, doesn't matter right now, it's there somewhere. Whether it's in the heap or stack doesn't matter for now, and I store there. Now I have B equals A plus 1, so I have to move 1 into some register, I have to load A from the memory, put it into another register, so R2, then I have to add it, and let's say I have to store the result back. The addition is available, as let's assume, in R2, and I have to store the result back in memory in the variable B. And the same template is followed here for performing the remaining mapping from IR instructions to assembly code, let's say. Are all of you with me till now? Notice that I am reusing these registers here, right? So I am overwriting the contents of R1 and R2 here, which means if you need a variable in future, you will have to again put it into some register from the memory, and that's the reason the simple code generator here just decided to store everything in memory so that it can be loaded from memory. Even if the register is written with something else, the variable's value is still available in the memory. I'm not losing its contents. Okay, so this is a simple translation to begin with. Now, okay, before the big question, can you compute the number of bytes and the number of cycles to execute this code? Number of bytes occupied by this code based on what you wrote in your cache memory, and the number of cycles required to execute this code. Let's see who comes first. Count the number of bytes, because that's what we would optimize, right? How do you say that this code is better than this code if I give you two code pieces? You have to use some metric and say, oh, this is better than this because it takes fewer bytes than this one to store, or if it is expected to take fewer cycles than this to execute, and so on. 42 bytes, okay, that's a candidate. What's your name? Nikhil says 42 bytes. Would anyone like to say Nikhil is wrong, or would anyone like to say Nikhil is correct? You also arrived at 42. And see, you are allowed to work in groups. Assuming that you are working on this, you are allowed to work in groups. You can find a friend, make a friend, and do it together if that motivates you to do things faster. Yes? Yes, we are just adding right now. Yes, we are very simple model. Right now we are assuming that each instruction is just executed one after another. Good question. We are not assuming anything special on the hardware's part right now. "42 bytes, any other answer? 25 bytes, okay. So 42 and 25. The 42 person I can see now looking at his notes suddenly. You have confused him. Can you count once more? I think 25 is not right. Can you count once more? How many cycles? 26. Any other answer? 28. Let's see, what do we have? Oh, I have 44 cycles written here. How did we count here? Let's just make sure we are moving towards 44, okay, even if we don't count exactly. What did we say? An instruction with 2 operands will take 2 cycles. So which one is memory? This one, right? Let me do some hacky computation here. I have 14 instructions, each of them have 2 operands, so minimum has to be 28. Okay, it can't be less than 28, and then some of them access memory. I'll add 2 for each of them because memory add instructions are supposed to take 4, right? How many are there? 1, 2, 3, 4, 5, 6, 7, 8. So I'll add 60 into 28, which means 42 at least. It's written 44. Oh, it's 44. Yeah, 28 plus 16 is 44, right? And space is 42 bytes. I think many of you came up with the same. Those of you who came with 25, do you see why is it 42 now? Yeah, okay. So let's say this is our current state of the program, and as one of you was pointing out just now, we are not assuming anything special on hardware's part here. This is a simple example for next 10 minutes, let's say. No, it stores in an address B. Okay, so it's storing the content of R2. Yes, value stored in R2 into, let's say, a memory location which is referenced by B. And again, we have abstracted out this information, like we ignored pipelining or any other special features here. We are ignoring whether the variable is on stack or heap, so heap accesses may take more time and so on. All that will come to slowly, will build up slowly. So by tomorrow you will talk about heap, stack, pipelining, everything. Okay, but that's later. All of you with me right now? Let's just move fast now. Can we do better? Can you suggest some optimization just by looking at this code, and what's bothering you the most? If you looked at this one-to-one translation, think about things that are bothering you, that why did I generate this stupid code? Just raise hand and say something that you think can be improved. And how would we measure improvement? We would measure it by counting the number of registers, the space and the time. Don't come up with a count right now, but what do you think is improvable here? Yes. Good. So you stored B, R2 into B over here, and you are going to immediately load the content again into some register, right? So what's your name? Arnav. So Arnav luckily tells me what is there on my next slide, I think. So the first thing we could do is, we can use registers better. If I know something is already there in a register, even if I have stored it into memory, I need not go to the memory to access it. I can directly access it from the register, because we know that memory accesses are costly as per our metric over here, right? So let's rewrite the code to use registers slightly better, and let's say here, since I have stored R1's contents into A, I already know that A is present in, no, what did I do better over here? Yeah, so I already know that A is there in R1, and hence I can avoid moving 1 into R1, I can move 1 into R2 and directly use R1 over here because it has A. So this will also do A plus 1, I know it, right? Similarly, if I have B already in R1 here, I can directly load the content of B from R1, I mean I can directly add it to the content of R2 which has C over there, and so on, right? So I have just seen that, if I am going to immediately use a variable and that variable is already there in a register, let me not overwrite that register's content, let me use another register and let me use that register in the operation that was using that variable. Okay, so this is an optimization. What did we improve by? Space, time, number of registers is still 2. Space, how much now? 33, okay. Time? Count. Why should only my brain work? (32). So improvement on both fronts. Okay, so space is 33 as per some calculation here, and time is 32. Are all of you with me? Okay, right. So how much did we, if I were to ask you, how much did we improve just by doing a small optimization here, which was use a register, if don't overwrite a register if the content of that register is going to be used immediately in the next block. How much did we save here? Percentage? 44 to 32, 42 to 33, roughly 25% saving, right? Just by performing one optimization, one simple optimization. And fine, this was a 4-line code. Here you will say, okay, I have seen like 10 bytes. Why does it matter? But assume you have a 4,000 line code, which is of typical IR size, let us say, for a small program, and you would have saved how many bytes? 40 bytes may you save 10 bytes, 4,000 bytes may you would save 1000 bytes, suddenly 1 KB saved, right? And this way you can keep building up, right? So just one optimization of this kind may lead to a significant improvement. That's first thing we see with this example. But now let's continue. Can we do better again? What's something that's still bothering you in this code? When I teach in a class, I usually have something called as participation credits, and those people who answer more get those PCs, and those PCs can be used to extend the deadline of an assignment later on, or get a coffee if you don't extend the deadline at the end of the semester, and so on. So these things motivate people, but maybe I can still give you PCs and we can have the coffee thing. I cannot give you marks for it, but still. Huh? So Nikhil has one. Who can improve this code next? Yes. Okay, both of you can say one by one. Sure. So Aditya says here that if there is a better instruction for adding 1, what is an example of a better instruction? Let's say if I have an increment instruction, if I say increment R1, it directly adds 1 to R1, right? I would save on space at least. Yeah. We can, if addition is known to be cheaper than multiplication, then I can replace some multiplication operations by addition. What's your name? Shreyas. Has any of you seen the actual circuitry for multiplication and addition? Can you confirm that multiplication is usually costlier than addition? Let's say integer multiplication, right? Usually it is. Okay. So, okay, here there is something more. Let's say I want to remove the redundant store to A. Where is the redundant store to A? So, those two are valid. They will come in the next slides. And can you identify a redundant store to the variable A here? Any store is a memory access, so it will take time. First one, right? I am storing R1 to A. Am I loading this A anywhere? No, I am not accessing this A anywhere. I am storing some other new R1 to A later on. That means this memory store was just a waste. Right? So that's, did this come to somebody's mind? You should have spoken. Okay. So if you do this again, you save a bit. Oh, this was done already. You save a bit. You would, let's say, move from 33 to 30 and 32 to 28. Still improvement. Okay. And can we do better? Well, the next thing is, let's take the suggestion from Aditya, select specialized instructions. So let us say moving 0 to R1 is same as clearing a register. It's at least a smaller instruction and one operand. So according to our heuristic, it takes fewer cycles as well as less space, right? And then for adding 1, move 1 to R2 and then add R1, R2. These can be replaced by increment R1 directly. You would even avoid using that register for that time being, right? And then you can, is there anything else we have used? Yeah, multiplication. Well, interestingly, you could have replaced multiplication with addition, but let's say we also have a shift left instruction. What happens if I shift the bits of a register by 1? The contents get multiplied by 2. Right? So if you see what I was doing here was moving 2 to a register and then multiplying R1's contents by 2 over here, which means I was doing a multiplication by 2. So I can replace these two instructions with a shift left instruction if it is available, right? How do you find if it is available? Yeah, according to the ISA. It's simple. It's just a finite list given to you by the hardware designer, let's say. Okay. So let's say I improved the memory usage by not performing redundant stores, and then I also have selected specialized instructions over here if they are available in the sheet provided to me by the hardware vendor. So what is the improvement right now? See, now it's coming into one block. How many bytes and how many cycles now? Where do we stand? 12? No, not 12. 21 perhaps. And if you are coming up with the wrong answer, you have probably removed the information about our metrics from your cache. Bring it back. So this says 21 bytes and 21 cycles. Can somebody confirm? Can someone come up with 21 and explain it to the whole class so that if somebody is doing it wrongly, we would all be on the same page again? How many bytes for the first instruction? 2, then 2, 4, then 4 plus 4, 8. Can you keep counting like this? Do we come at 21? Is it right or is there some mistake? It's right. And 21 cycles? Yeah, okay. So some of you are able to arrive at those numbers, which means probably there is not a typo. Okay, can we still do better? We have come from 44, 42 to 21, 21, 50% improvement. Can we still do better? I told you the first session is very simple today, but see the impact. What can you still do better? And I would allow you to make assumptions. Let's say somebody had to make an assumption that an increment instruction is available, right? You are allowed to make assumptions like this and tell me. Store, okay. Oh, cool. Yes, I am storing something to B and I am not using B anymore. Was I using it before? Maybe we were using it before and it has become redundant now. Not sure. Yeah, see, earlier it wasn't redundant. We were storing it here and then we were loading it from here. But we somehow changed these instructions now and we have got one more redundant store. Good point. So Jayashree got one more here. Anything else? We are here right now. Yeah, sure. We are not using C as well. What's your name? Srinivas. So Srinivas and Jayashree, as they said, we have more redundant stores. See, things like this should tell you that you may want to perform a given optimization again at some point of time. If you remove redundant stores only in the beginning, you are able to remove only A's store from there. If you perform that optimization again, you may get more opportunities over here. But you can't say that I will always perform it at the end, because when you saw removing A store gave us some more opportunity later on in between, right? So you may want a typical compiler will not perform a single pass of any given optimization. It will perform it again and again and again based on some mental model of, oh, when will it be again useful? Okay. Any other improvements? Number of registers, we are still stuck at 2. I'll tell you by the end we will have 1. Okay. Any thoughts on that? Sure, we'll probably come to that. So if you see, let's look at this code to realize if a single register is enough. What am I doing over here in general? I'm just adding 0, which is redundant. Then I am multiplying by 2 at the end. I am incrementing something here and then multiplying the content of B with the result of adding 1 to the content of C. So that's the optimization here. But then see, it's not easy to look at the source code and understand what is it doing and replace it directly. So we have to come up with since here it's just 4 line, you may be able to see what is the operation. We will end up coming up with a small sequence in the assembly which will also do just that operation, as Jayashree was trying to point out over here, right? So now let's see what comes here. Oh yeah, so exactly what I said just now. We are clearing a register and then incrementing it. Instead, we could have just moved 1 to the register where we are going to store 0 plus 1, right? This is essentially 0 plus 1. So if I just look at these two instructions, what I need to do is to add 1 to R1. That's what I am doing here, right? So I could have directly, see, I have undone something. That also happens. I came up with a sequence of instructions by selecting them from the hardware, which I thought are better, but now I see some more opportunity here and I can remove those instructions. Don't be too emotional about, the compiler is not too emotional about the instructions that it chose to generate, and it can decide to move from here to again a move instruction, for example, because it looks better at this point, right? So it may directly try to move over there, and now, okay, 1 byte we saved further, still improvement. And we could have done the same thing for B, let's say, assuming B is not used in future, which you people found out, B was not being used in future. So I can directly propagate the constant 1 over here. I don't need to store B, store R1 into B. I know R1 contains 1. I can directly propagate that 1 over there in the future wherever I was using B. So now we are Finally, we move from 2 registers to 1 register if we do this. If we propagate the constant, we don't need to store it into a register over here, and then we are into 1 register, 50% improvement again, okay. Forget about percentages, but it looks interesting. Can we still do better? I want these 2 boxes to become same size at the end. Give me one more instruction out. Achieving the last mile in a long marathon is the hardest. Is the C variable redundant? Yeah, that you can assume, let's say that, oh, if C is also not being used, I can avoid storing C R1 into C, right? And which means you can directly use R1 over this. Can I just delete it? Right? So there is one more here. Okay, sure. So let's say, since we don't have it for now, what's your name again? Keith. So as Keith said, we could have assumed that C is also redundant and removed its store. Let us say there is some usage of C in future and we can't do it. Okay. Let us say, just because on my slides I don't have it right now. So let us say that's not possible, because there is some instruction later on that uses C. I can still do something better here, which is, if I have an store immediate instruction which allows me to store a number directly to a register, to a memory location, instead of loading the number into the some register and then moving it to the memory, I could have directly stored 2 into A instead of moving 2 to R1 and then moving R1's content to A. So now again I looked at my ISA, saw is there a store immediate addressing mode wala instruction available. Since it was, I could replace these 2 directly with that instruction. Okay. Where are we now? How many registers? 1 space 11, is it? Yeah. I mean 2 plus, yeah, I think 11 is right. Yeah. And then time is 13 over here, right? So now, assuming no other special instructions and no new knowledge about past or future instructions, which means C might be used in future, A might be used in future, can you still make it better? Now think a bit out of the box. Yeah, somebody was saying something, please suggest. Someone was saying, just speak out, it's okay, you might be wrong in the worst case, what's the problem? You can load the incremented, but you have to increment it, right, somewhere. You usually, okay, so let us assume, which is usually a good enough assumption, a representative assumption, that you can't directly operate on memory. Okay. You have to bring the memory's contents to the CPU in order to perform arithmetic operations on them. So there is no increment of a memory available in my hardware, let's say, which is typically true, because it requires a load and a store and so on. So now I'm just putting these restrictions here, no other special instruction and no new knowledge about what happens in future or what happened in the past. Omkar, yes. Yes. Yes, if you knew that B is dead after this point. B is a local variable, right? So Omkar's point is, okay, let's make it a bit more clear. In fact, just saying B is dead, B is not live as per live variable analysis is not enough. You also have to see that B is not a global variable. Let us say I performed liveness analysis in a local scope, inside my current basic block or inside my current method, I have to make sure that the variable b cannot be used outside this basic block or outside my scope of analysis. We'll in fact start talking about this aspect more. What is the scope of analysis and compilation? We will talk about this more on Wednesday when we talk about JIT compilers, but I hope you see that. So this any of these transformations is valid under certain assumptions, and we have been making those assumptions. The assumption was assuming B is not used in future. That was one assumption, and by future we mean, oh, nobody can access it outside this scope, let us say. Okay. Yeah, let's come back. Any other improvement? I would like those of you who were talking about pipelining to think more now. Hint. You can even say, oh, if this happens, then I can optimize this code more. How many cycles did we say does it take to perform a store? 4 cycles, right? 4 cycles to perform an instruction involving memory access. I have 2 instructions with memory access next to each other. This was hint number 2. Can you do something better? Yes. What would you like to reorder? Yes, you can push store a comma 2. And why is it valid? Why would it be valid to push this instruction above somewhere? I mean, forget about whether there is pipelining or not. Let's first see, is it okay if the compiler schedules this instruction before these 3 instructions? Yes, because this is independent. So we would talk about a dependence analysis in tomorrow's lecture, mostly sometime in today or tomorrow's lectures, where we'll say, oh, if an instruction is independent of the others, then you can schedule them in any order, right? Is this instruction independent of this? Yes, all of them. So which means I can schedule it here, anywhere, doesn't matter. Now if the compiler sees, or now if let us say I have the knowledge about the current pipeline used by the hardware, and I see that, okay, moving 2 store instructions as apart as possible is useful, because one of them might have finished by the time you come to the next one, right? Assuming here that this takes 4 cycles, and until this one finishes, if you cannot start the next one, you will have to wait, even if this is independent of the previous one, right? So just by looking at our metrics, oh, maybe 1 register, 11 bytes and 13 cycles looks like the best we could have done for this small piece of code. But if you not so fast. If you look at the hardware, this instruction sequence might be better than this instruction sequence, and that's what is meant by instruction scheduling, which we would learn, as I said, sometime in these sessions, right? So you can schedule an instruction to happen before some other instruction, and that's also done by compilers. All of this is done by compilers while generating instructions for the low level, okay? So, and you can start thinking about multi-threaded programs and so on at this point of time, that, oh, what if I have multiple threads available? Can I schedule different instructions across different threads, which probably can run on different hardware itself? Will I be able to speed things up? And hence parallelization is something which compilers achieve very well as well. I'll take a small digression here. How many of you have written programs in any concurrent programming framework? Let's say OpenMP, or Krishna will use IMOP, I'm sure, in one of his lectures. Yeah. Pthreads, yeah. So you might have written even OS programs using pthreads, some of you. Anybody else who has used pthreads? Yeah. How many of you have used, let's say, multi-threaded programming in Java? Yeah, we have some people. Good. So I hope you see that writing concurrent programs has not been an easy task, or it doesn't look as easy as sequential programming. Do you feel that too? At least some people said yes, those who have written programs. So, you know, many universities around 15 years ago, particularly MIT, CMU and so on, these universities experimented with the idea of teaching parallel programming or concurrent programming, if you distinguish them, as the introductory CS 101 course. Okay. They thought of teaching parallel programming first and then tell that, oh, sequential programs are just a special case of parallel programs. They miserably failed. Now they don't teach it as CS 101, they again teach C or C++ or Python or some such language as CS 101 without multi-threadedness involved and so on, right? So people have struggled a lot with writing concurrent programs, and people still rely on compilers or automatic parallelizers more than humans for parallelizing code. Okay, so Professor Krishna, who teaches you towards the end, will talk more about it, but I just want to show you here is instruction scheduling is a compiler's is a very compiler specific problem. A compiler can schedule instructions by analyzing dependencies, and then the compiler can also parallelize these instructions because it knows about the hardware, right? So this is something also which is typically done and probably done better by a compiler than a human. All right. Any questions? Okay, let's go a bit more and then we will take a break. I hope you are not as tired as me, but this is what we are learning over the next few sessions, right? How do we generate code like this was easy, one-to-one mapping, but then how do we go from here to here? How do we reduce, how do we make an efficient use of registers? How do we choose instructions which allow us to access memory as fewer times as possible? And then we will make up a model here, then we will say, oh, memory has heap and stack accesses are faster than heap and so on. So how do we generate instructions such that more accesses are from the stack than from the heap? We will also see how can you optimize cache accesses, because cache access is faster than memory. So how can you keep things that will be used in future in the cache and so on, and all of this is done by compilers in the low level optimizations and code generation phase. We will also see some basic idea of instruction scheduling, how to decide which instructions to schedule at what point of time. Okay, so this is what we will learn in the next 7 sessions. So let's just talk about instruction selection a bit and then we will take a break. 10:30 is the break, right? Yeah, so we'll finish this and then take a break, right? So low level IR is different from machine ISA. You can have different backends here. Each backend can come with different ISA, right? How many of you have seen some form of assembly? Yeah, some assembly, x86, ARM, whatever. Many of you have. Those of you who haven't seen it, you might have at least read. I mean, by seen I meant you have actually seen some code, let's say, but even if not, I hope you have had some exposure. You have had an organization or architecture course where you have seen what is the format of CISC or RISC instructions and so on. Is that the case? Okay, if not, we'll just have a quick look. Okay. So an IR is usually simple. It has a uniform set of operations, as you have seen in the last few lectures, let's say, and ISA has many specialized instructions that we could use, floating point separate instruction, then integer addition, for example, and so on, right? And often a single assembly instruction does the work of several operations in the IR. It's not always that one IR instruction, 10 assembly instructions. It can also go the other way. If you are working with a vector processor, you may have special instructions in that ISA to work with vectors. Instead of moving 4 things one by one in a loop, you may be able to have a single instruction and move 4 things from here to here. 4 registers to 4 registers, let's say, or 4 memory locations to another 4 memory locations and so on. Okay. So, and then yeah, we have CISC and RISC architectures and so on. So the easy solution is, as I said, map each IR operation to a single instruction in the beginning. That's what most compilers do. And then include memory operations, because you may have variables stored in the memory. So x equals y plus z may require 2 movements from the memory in the beginning, then an addition in the CPU, and then one more movement at the end to store the result. I am switching, well, different architectures will have different conventions, whether move means move from here to here or here to here. I guess in this code example we are assuming it's from here to here, but these are contextual. I am not specifying a given hardware right now, right? And there is inefficient use of ISA with just a one-to-one translation. So in this case, for example, if the ISA had an add instruction that allowed memory things directly, as one of you was trying to say, we could have improved this instruction sequence and directly added, let's say, I load Y into some register and directly add that register to the memory Z. Okay. And then there are other interesting things. When you select instructions, there are other properties of different instructions that come into picture here. Let's look at some examples. What will this statement do? Let's say %EAX is a register. So those of you who have seen x86 assembly, there are registers like EBX, ECX, EAX and so on in x86 assembly. So let's say %EAX is just a register. Okay. What would this instruction do then? Clear the register. If you XOR something with itself, 1 1 0 0 0 0, you will just get all zeros, right? What if I had chosen this instruction? So see, we are now talking about the case where I said I'll do one-to-one mapping, but I have two options. Because the hardware vendor's specification tells me that this instruction also clears a register, this instruction also clears a register. I have two options now. How do I choose? So why would I choose, let us say my compiler chooses this instruction instead of this. Why do you think I would do that? Yeah, why so? Or I didn't tell you anything about cycles till now. Maybe, okay, let me be devil here. Let's say both of them take the same number of cycles. What else could be a reason? Both are using one register. Could be, yes, that could still be an assumption that, oh, maybe it's actually true that one of them is faster than the other. In terms of space, how many registers do you have? Let's say, okay, let's say I have 16 registers on my machine. How many bits do I need to represent a register as part of an instruction? 4 bits, right? And 0 is a byte. Let's say I work with an architecture where the unit of memory is byte. Okay, so let's say 0. If I want to say 0, I can't just use 1 bit. I have to store at least 1 byte representing 0. Okay, 0 0 0 0 0 0 0 0. So now, how many bits will be needed to store this instruction? 4 bits are needed to choose an instruction, choose a register. 1 byte, so 8 bits here, 12, and whatever, assume this is something 1, right? What about this one? Fewer bytes, right? Which means you can even just use 1 byte to store both the operands over here, right? So maybe from that perspective, the compiler should decide to use the first instruction and not the second instruction. Similarly, maybe bitwise operations are faster than moving a byte from moving a byte to a register and so on. Okay, so depending on these, you may have, when you are presented with multiple options, as when I say you are the compiler, when you are presented with multiple options, even one-to-one mapping is not a straightforward problem. You have to again come up with some cost metric and decide which instruction to choose. Okay. Yes, then there are architectural differences in the ISA. So what is R and C in RISC and CISC? Reduced and complex. So what is reduced in reduced instruction set? What do we reduce in RISC processors? Size of ISA, the number of, very good, the number. So as Kirt says, we have fewer instructions available in a RISC computer. Typically, the specification will take less space for you to read or for you to print, for example. Whereas in a CISC computer, you may have more instructions. If I have more instructions, what do you think I will have in those more instructions? What kinds of instructions would be there? Like? Yes, so you may have separate specialized instructions, right? Whereas in a RISC computer, you may have to work with a smaller set of instructions. You may have to choose specialized set of instructions instead of being able to many times find a specialized single instruction for doing certain tasks, for example, right? So, for example, this is typically true. RISC systems would require registers for arithmetic operations because they have fewer instructions. They won't add up immediate operand instruction, memory access instruction directly to the ISA. The design is simpler. which means if registers require arithmetic operations require explicit registers, that means for performing any arithmetic operation you have to move things from the memory to the registers first, right? And in a SISC computer, so in an example could be, oh, I have to first load the content of something into a register before adding it, instead of adding it directly. Whereas a SISC computer may have more instructions, well, complex or not, but it may have more number of instructions for sure. And let us say typical SISC computers allow you to access memory directly, or at least one operand of an arithmetic instruction is allowed to be a memory access directly. Okay, so you may be able to directly say, oh, add the content of the memory location obtained by adding 8 to the content of this register to the content of another register. You may not have to load it, so you may be able to generate fewer instructions for this. Of course, each instruction may grow in its length because it may allow you more kinds of operands and so on. All of you with me? What class does x86 come under? Typically, I mean, of course, these are not just fixed labels. You can say something is more complex than another. These are relative terms, but which one? CISC. And what about this guy? So ARM is a RISC processor, if you hear that term, right? And so on. Which means your instruction selection choice. If I am writing a C compiler, GCC, or rather make it simpler, I am writing the code generator or even the instruction selection pass for GCC. I have to choose, or I have to use different metrics to choose instructions for different architectures. So in a typical compiler, we'll probably open up some compiler's code in one of these sessions and see, but typical compilers will have some parts of code generator that are common. Let us say register allocation, no, not register allocation, that also depends on the architecture, but let's say there are some dead code elimination kind of optimizations and so on, which are machine dependent like we saw. So some implementations of these optimizations can remain independent of the architecture, but some things like which instruction to choose, which register to allocate and so on, that part will be coded differently. So you will see some generic routines in a specific compiler backend, and you would see some specific routines. Let's say there is a file instruction selection.h, and then there is a file instruction selection underscore x86.h, and there is a file instruction selection underscore arm.h. Don't be surprised. You should know why there are different files, because there are things here that depend on the architecture. Make sense? Okay. And then selecting instructions with minimal cost, as I said, how to find which patterns are the best, it's not usually easy. How to, the translation may not be one-to-one, it may not even be linear as we have seen here. So the idea which we would go in this course would be to generate a simple mapping and then perform peephole optimizations. Okay, peephole optimizations are the ones that you were performing before. When I was asking can we do better, you were looking at just a small code sequence and deciding whether I can perform some optimization, right? What is a peephole? It's just a small window, let's say. You're not, so when you perform data flow analysis, what did you construct it first in the lectures in the last week? A control flow graph, right? So you first obtained a control flow graph, and a control flow graph was a representation of multiple basic blocks in a program. Typically a peephole optimizer will look at just the current basic block, not even two basic blocks most of the times. Okay, it would just perform optimizations within a basic block. See, all of the optimizations that we performed just now, we improved code so much without looking across basic blocks. They were just a linear sequence of instructions. There was no jump over there, right? There was no out jump, in jump. So those 4 IR instructions from where we began were in the same basic block. It's a valid thing to assume there, right? So there are several peephole optimizations, and we would start learning about them, and then we would perform register allocation after the break. Any questions before we go to the break? So what I would like you to utilize the break for is, of course, feel free to talk to me and talk to others, but if you haven't been able to set up the assignment code on your computer, please take your friend's help or just follow the instructions. Now, do you have, all of you I hope have the instructions that were sent, right? So there is a Google Drive link from where you have to download something. Why? So what are we going to do? Let me give you a 2-minute introduction to what are we going to do in those sessions. We have some assignment code available. Let us say if you had 10 days in this course, I'll give you an assignment and say that, oh, this is a compiler framework or an analysis framework where this is the input format of the intermediate representation that comes in as a program, and for those programs you have to write a pass that performs register allocation. That is, it replaces, let's say, all variables with some registers, and I give you some constraints. Oh, you only have 4 registers, some register can be used only for floating point, some register can be used only for storing the return value of a function, and so on. So I'll give you some of those constraints, and under those constraints I'll ask you to write a pass, some code which would be capable of taking any valid input program and perform register allocation based on the constraints. Okay. So now, since we don't have that much time, what I did was I have taken a previous student submission on such an assignment and we have it available, but I am teaching you register allocation in the next session, which means you would be able to you would be able to play with it, give it a test case, write a program and see what register allocation does it do. If time permits, we would see how can you change some of those constraints and modify the code, but no, if not, at least you have an assignment that you can use to play with register allocation. Okay, so that's what we would do. And since all of you have different laptops, different operating systems, what we have done is we have Dockerized this assignment code and we are providing it to you as a Docker file which you can use to build a Docker image. What does Docker do? Has any of you heard of it? Yeah, it virtualizes things. So it basically it's a snapshot of some software, but you can build it on your machine based on your hardware. It will allow you to create a new image. Some of you would have used VirtualBox and virtual machines. At least the goal is similar. Okay, so we have a Docker file. It's not too tough, but don't worry about. I mean, I'm not going to teach all of it right now, but it's not too tough either. So there is a file which has some instructions that will allow you to spin an Ubuntu image on your laptop, let us say, right? Whichever OS you have, Mac OS or whatever, if you have Docker installed and you follow the instructions, you would have an Ubuntu Linux image. In that image, everything is already installed. Java is installed, I believe Python is installed. So whatever we would need is already installed in it. Even our assignment code is copied in it. And when you load it up, you would create a container. So an image is just a static copy. When you create a container out of it, you have a working copy now, right? In that working copy, you can make changes and so on, which we'll do. We won't make changes directly. So if you don't know terminal, Linux, doesn't matter. We would directly load it up in VS Code and work with it. How many of you have not used VS Code? Some of you. Have you used any alternate editor or IDE? Direct terminal VS Code is fancy for you. You don't worry. But if you have not used any IDE editor and VS Code and terminal, then you will have a bit of pain, but fine, you will learn it, right? So it's just a GUI environment in which we'll work for today and tomorrow. Okay, so this is what we'll do. If you have not been able to do some part of the break, maybe utilize either now or after the lunch and set it up on your machine. All right, any other questions? Okay, people optimizations after the break. You don't seem tired enough. You don't want a break? No, it's okay. I'm happy that you have had a good rest on Sunday. I don't that urge for a break, in you right now, which is good. Which means you would be able to learn more today.